Hello, welcome. In this video, we're going to talk about drawing skeletal formulas, which are also known as line angle formulas. This video segment follows from the previous video segments, which were numbers 305, 306, and 307, where we looked at other ways of drawing organic molecules, including condensed structural formulas and Lewis structures. Lewis structures showed the greatest amount of detail explicitly about our molecules. Condensed structural formulas began to abbreviate structures by omitting many of the covalent bonds and not showing lone pair electrons. And then skeletal formulas are going to be our most abbreviated method in our toolbox of drawing organic molecules. As we get deeper and deeper into the field of organic chemistry, we will see that in most cases, in the real world, the preferred method for drawing organic molecules are indeed these skeletal formulas, which are also known as line angle formulas. And the reason they're so popular is because they allow us to convey a lot of information, often about very complex molecules, in a very simplistic, abbreviated manner. What we see here is an example of a skeletal formula or line angle formula where you will notice that rather than seeing atoms shown, instead it's just this zigzag line. By the end of this video, we will know how to interpret what is meant within those zigzag lines or other features that we may see pop up within skeletal formulas. So let's go ahead and dive in a bit more. We'll begin by going over the basics of how to draw skeletal formulas, also known as line angle formulas. As we discuss this, I'm going to use this structure here, this line angle formula or skeletal formula, as our example to fill in the parts and pieces of this structure, recognizing what is meant by this kind of weird shaped N is what it looks like at the moment. The first thing that we need to know in order to interpret line angle formulas or skeletal formulas, as they're also known, is that every bend in the line and end of a line represents a carbon atom unless a different atom is shown there explicitly. So let's go ahead and fill that in as one of the things that we need to recognize in interpreting these is that all bends and ends of a line represent carbon atoms unless a different atom is shown. So how can we interpret that information for our example here? Well, looking at our example, we have an end of the line here, which we can infer is a carbon atom because all bends and ends of the line represent carbon atoms. Second piece here, that bend has to represent a carbon. Right here is a bend, so that has to represent a carbon. And then here's an end of the line, that has to represent a carbon. So every time you see a bend in the line or an end of the line of the zigzag, that's going to represent a carbon atom unless you see a different atom shown explicitly there. So if there was another atom instead of the carbon, you would see it listed there. You see an O for oxygen, an N for nitrogen, an F for fluorine, etc. And that would tell you that at the end of the line, rather than there being a carbon atom there was instead one of those other heteroatoms. So all bends and ends of the line represent carbons. So based on interpreting this structure, we can determine there are 4 carbon atoms in total in this particular molecule that we have shown. Now from there, what we can show from the lines that we have here, the lines are going to show the connections between atoms, meaning that the lines represent our covalent bonds. So lines within our structure show covalent bonds. And those lines represent how many covalent bonds there are. In other words, a single line refers to a single bond. A double line represents a double bond. And as you might be guessing by now, a triple line represents a triple covalent bond. So in the case of the structure here, what we can determine is that every single bond within this molecule is a single covalent bond, since all we see here are single lines connecting our atoms, not double lines, not triple lines. All right, next point here, as we go through the process of interpreting skeletal formulas, is that unless indicated otherwise, every carbon atom we can assume is fully saturated with hydrogens to fill its complete octet. So unless other atoms are shown explicitly, such as oxygens or halogens or whatever else, so unless other atoms are shown explicitly, we are going to fill all octets on carbon by adding hydrogens as necessary. And we can do this because we know that all carbon atoms, as we've seen time and time again so far, is that all carbons need a total of 4 covalent bonds. So in other words, whatever covalent bonds are missing from each carbon atom that we see, we can assume that the octet is filled for that carbon by filling in with hydrogens as needed. So for example, I'll do bright green here. At the left-hand end of this molecule, our carbon right here has just one covalent bond shown explicitly to another carbon. So what's implied here is that there have to be 3 bonds to hydrogen to fill the octet on that particular carbon. So we could fill that in as CH3 there to give the 4 total covalent bonds, with 1 covalent bond going to the next carbon in the chain and 3 going to the hydrogen atom. So that's what we're saying here, is that unless we see other atoms shown explicitly as lines going to the next atom in the chain, or oxygens or other heteroatoms filled in, we fill the octet on every single carbon atom that we see by adding H's as needed. So that's why we filled in 3 H's there to equal the grand total of 4 covalent bonds needed by that carbon. Next spot here, right here at this carbon has 2 covalent bonds to here and here. And so to fill its complete octet, it would need to have 2 hydrogen atoms because it already has 2 of its 4 slots full. So 2 more slots would have to be filled by hydrogen to give it its 4 covalent bonds that it needs in total. Same situation here at this carbon. That carbon has 2 covalent bonds shown in gray going to the adjacent carbon atoms. And so that would leave that carbon needing 2 more covalent bonds filled in by 2 hydrogen atoms there to give it its complete octet. Then at the right-hand terminal of the molecule here, fill in CH3, indicating to us that this carbon is directly bonded to 1 other carbon atom and 3 hydrogens. So based on the info that we've seen so far, what it's looking like in this structure at least is that when we're drawing skeletal formula, the carbons are implied and they're shown as the bends on the line and the ends of the line. And the hydrogens that appear are also implied, where we're using the hydrogens to fill in the octets on the carbon atoms as needed. And this is going to be able to be generalized that carbons will never be shown. Instead, carbons represent the ends of the line and the bends in the line. Hydrogens are omitted in the skeletal formula unless the hydrogens are bonded to a heteroatom. So show hydrogens only if they're bonded to a heteroatom, meaning an atom other than carbon. So show hydrogens only if they're bonded to a non-carbon atom. For example, if you had an OH group in a skeletal formula, you would need to show that hydrogen explicitly because that hydrogen is not bonded to a carbon atom. Instead, it's bonded to an oxygen. So that's the rule for showing hydrogens. Show hydrogens only if they are bonded to something other than carbon. Hydrogens that are bonded directly to carbon atoms are never shown. And likewise, as a broader point here, as we think about how we show different atoms, we commonly also see within organic molecules nitrogens, oxygens, halogens, and other types of so-called heteroatoms. And when we are drawing line angle formula, we do show explicitly all heteroatoms, oxygens, nitrogens, sulfurs if you have one, chlorine or other halogens, etc. And what we will do for those is at the ends of lines, if there is a chlorine instead of a carbon, fill in Cl at the end of the line or at the bend in the line, and that will indicate that there is a chlorine there instead of a carbon. And we do show hydrogens that are directly bonded to those atoms as we looked at a little bit above. So let's apply this. So I'm going to shrink this down a bit so that we can then focus on an example problem. With no further ado, let's pull up the example problem. In this example problem, which is a key skill for organic chemistry, we are asked to convert the Lewis structure that we see lower left into a line angle formula or a skeletal formula. So how are we going to go about doing that? We keep in mind the rules that we see up top there in black, and we will begin at one end of the molecule. Start from the left, start from the right. It doesn't matter. Whichever end looks easier to you is where I would start to get some early wins here. So I'm going to start at the left-hand end of the molecule here with a CH3. We keep in mind that all bends in the line and ends of the line represent carbon atoms, and that we assume that the octet is filled on each carbon via hydrogen, so we don't show hydrogens explicitly in line angle formulas when they are bonded to carbon atoms. So we can show this as the end of a line here representing a carbon atom. So right there, where I've got the arrow pointed toward, would be our CH3 group from our starting structure here. So what I am highlighting in pink here in our starting structure will be represented by that left-hand end of the line right here as our CH3. We come to the next spot in the line. Connected to that CH3 group is a carbon, and that carbon's connected to two oxygens here and here. So we're going to fill in that carbon atom as the other end of the line. So the other end of the line here, that end right there, represents the next carbon in the chain. And I'm going to highlight that next carbon in the chain here in blue. And I'll put a little blue dot on it there as well. And color coding, I'll put a red dot on the carbon that was shown in red or pink highlighter over here to show that those two are connected to one another. One is the end of the line, that's the CH3 group at the end. The other is right here, and we're going to make that into a bend in the line because that carbon in blue is not at the end of the chain, but instead it's here in the middle. So we'll show it as a bend, and to show it as a bend, we take our line and we bring that line back down to make a zigzag pattern. And that particular carbon that we highlighted in blue here, that carbon is directly connected to an oxygen here, and it's directly connected to an oxygen coming up this way as well. Now we have to show the oxygens explicitly because those are called heteroatoms. They are non-carbon, non-hydrogen atoms. So we show that explicitly here. And I'll highlight it in yellow to indicate what we're referring to here and here. And we show that line going to it, indicating there's a single bond that connects the carbon to the oxygen. That's the carbon in blue to the oxygen in yellow. And then this carbon in blue is also connected to this carbon-oxygen double bond here. So we go ahead and fill that in by filling in a double bond here. So double bond like so, with an oxygen up there, up top. I'll show that in highlighter here as well to get myself color-coded and get things oriented there. Don't show the lone pair electrons. Lone pair electrons are omitted in skeletal formulas. So we do have to show the double bond here to indicate there's not just a single covalent bond connecting the oxygen, there's two. And then we show that oxygen up top here explicitly because heteroatoms are shown always as we saw up here in the rules. So we fill that in. We've got our carbon that was double bonded to the oxygen in green. Going over to the right, zigzag line to our oxygen. End of the line there is filled in as an oxygen. Since there's not a carbon there, instead there's an oxygen. Then we come on along through the chain, zigzag line. So we had zigzagged down, now we're moving back up. to our next carbon atom in the chain there, and finding a fun color to use for this, or not so fun, I'm going to do gray in my progression here. That would represent this carbon atom right here. And that carbon is directly bonded to 2 hydrogen atoms here and here. Hydrogens that are directly bonded to carbons are implied because we have to fill the octet implicitly on these line angle formulas. So that's why I'll put a gray dot there just to indicate that that's filled in like so. We come to the next spot. So we're going to do a bend in the line. Bend in the line comes down like so to make our zigzag pattern continue. And we'll fill in the next spot in the chain here with our CH2 group in yellow. I'll fill in a yellow dot there to represent that carbon in yellow here in our line angle formula. It is bonded directly to 2 hydrogens, so those are implied because carbons that are directly bonded to hydrogens are what we're using to fill the octet on those. And so we don't have to show that explicitly. And then coming along through, that carbon is directly bonded to a nitrogen atom. So what I'm going to do is in my sketch here, draw my zigzag line on up, and at the end of the line put in a nitrogen because there's a nitrogen there instead of another carbon. So our yellow carbon, CH2 right here, directly bonded to a nitrogen. Coming to here, I'll highlight that nitrogen in blue to keep it color-coded to match everything else. And that nitrogen is directly bonded to 2 hydrogen atoms, and we do need to show those 2 hydrogen atoms explicitly. So I'm putting an H and H there because remember that hydrogen atoms that are bonded to non-carbons are shown. We do show those hydrogens, so we plug in those hydrogens there. We do not show lone pair electrons ever when we're drawing line angle formulas, so I'm not going to put lone pairs on this nitrogen or the oxygen atoms over here. I just leave it completely as is. So with this, we can fill in our complete structure here as a line angle formula, giving us our solution to this, recognizing that our molecule has a grand total of 1, 2, 3, 4 carbon atoms. And the starting structure is 1, 2, 3, 4 carbon atoms in the final product there, where each end of the line, each bend in the line represents a carbon unless something else is shown there. And in several of these cases, like here, something else is shown at that bend in the line, and therefore the bend in the line doesn't represent a carbon. Instead, it represents what's shown, an oxygen. Or at the end of the line here, there's not a carbon and a nitrogen there. Instead, there's just a nitrogen. That's a common mistake that people run into, is they assume there's a carbon right here where my laser pointer is, in addition to the nitrogen. It's really just a nitrogen on there. So you have 1 carbon right here, that was our CH2 carbon, and then it's directly connected to the nitrogen. So don't fall into that trap as you are drawing line angle formulas and converting between line angle formulas and Lewis structures. One of the key skills that you need to master.